Welcome to another episode of AI with Sally, a New York Times podcast that brings you inside my conversations with luminaries of the AI chip industry. Today's episode is brought to you by our sponsor, Credo Semiconductor. AI training clusters are scaling to hundreds of thousands of GPUs and beyond, and the network is under pressure like never before. In this episode, I speak with Don Barnetson from Credo Semiconductor about how reliability is crucial given that crashing a training run can cost millions of dollars. Credo has spent nearly 2 decades developing some of the industry's fastest SERDES and building active electrical cables, or AECs, to keep AI infrastructure running at peak performance. In this conversation, we'll dig into the networking reliability issues that come with scaling AI, why reliability matters as much as bandwidth, and how Credo is taking on this problem with copper. Here's my conversation with Credo Semiconductor's Don Barnetson. Don, welcome to the show. So we're going to talk about network reliability in the data center today. This is obviously super important as cluster sizes get bigger and bigger. We've all seen the headlines about how big these AI clusters are going to grow. From your perspective, what does growth like this mean for network reliability?
Sure. Well, first of all, thanks for having me.
Of course.
AI has introduced a lot more network complexity than we've had in the past. So in the past, in general compute, we just had one network, a front-end network that ran a TCP stack, which was really, really robust. Basically, each node would keep a copy of the packet until they got an acknowledgement back from the next node. And so it wasn't very sensitive at all. AI added 2 more networks. It added a scale-out network, which spans the size of the data center. So it could be 100,000 or perhaps in the future 1 million GPUs. And it added a scale-up network, which today spans the size of a rack, perhaps in the future might span out to a row scale. Both of those networks run much, much higher bandwidths. The scale-out network is about 10 times higher than the front-end network, and the scale-up network is maybe 100 times higher bandwidth. And so they're not able to use these very robust protocols. They use a protocol more like UDP, where you basically send and forget, and the network's job is to deliver it with 100% fidelity. And so problems really start to develop when the network isn't able to deliver these packets with 100% fidelity.
Wow, okay. We also, when we're talking about training runs, we really need to keep the compute fed and keep everything connected. If something goes wrong, these training runs cost millions, or they can cost millions or more. If something goes wrong, there's an awful lot at stake. What happens if there is a problem?
Yeah, so the operation of these data centers is sort of a burst of activity with infrequent maintenance windows. So you do a burst of activity that today runs for about 30 minutes at a time. And so during those 30 minutes, you're forward propagating and back propagating data in order to train your model. And at the end of the 30 minutes, you then basically download the contents of the HBM to non-volatile memory, to flash memory, so that you create a checkpoint so that you can recover if something goes wrong. So in large clusters, what we see is those training runs only succeed about 80% of the time. So roughly 20% of the time, something goes wrong, typically in the hardware of the training cluster, which causes that training run to crash out. And so those crashed out training runs are simply lost. And in these large cluster, a crashed out training run, as you point out, can cost hundreds of thousands of dollars.
Yeah.
It's a really big deal.
It is a big deal, isn't it? Right, tell us a little bit more about soft errors and what that means, because I think we're going to talk more about these types of errors, and I want the audience to understand what that means.
Yeah, totally. So in the scale-out network, we're using UDP traffic, which is a send and forget traffic. And so if you're not able to deliver the packet with fidelity, then the other side has to send a request to replay back, which is extremely disruptive, and it can effectively crash out the training run. And so in optics, historically, we've worried about hard errors. So hard errors are lasers that have died, or things that are dead. But soft errors were really masked by the TCP protocol. In the back-end network, what we've seen is that soft errors happen at kind of unexpectedly high rates. So when we're sending data on an optical network, we're typically running a forward error correction, what we call a FEC algorithm, which is able to correct a reasonable number of errors. So we send data in frames of about 5,000 bits, and we're able to correct up to, say, 15 errors in those 5,000 bits. But if we get more than 15 errors, we get an uncorrectable, or what we would call a post-FEC error. The hosts are designed so if they see a couple, or in this case actually 3 post-vec errors in a row, they've decided that the link has become unhealthy. And they will issue a command to reset the link, or what we call flap the link. And so when you flap the link, you take the link down for, say, 15 seconds or so. But when the link comes back up, it's only come back up at layer 1. We've got this entire OSI stack that has to reconverge. And so in order to re-advertise itself, to sort of reconverge with the BGP protocol, we end up spraying maybe 500 million packets all around the network each time this happens. And you can imagine the worst case is where a link doesn't just go down once. The link might be unstable. So it's almost like you have a noisy neighbor. So maybe every few seconds or every few minutes it's flapping. And in that case, we've got a real big problem because we're spraying all these packets all over the system, and it's distracting us from being able to complete our normal workload.
I mean, this is a key cause of training run failures, and this is really bad for utilization of the cluster overall, right?
It absolutely is, yeah. So if you're only getting 80% utilization, you're wasting 25% of your electricity, you're wasting 25% of your depreciation. It's a really, really big deal. And so we've been working with our large hyperscaler customers over the last couple of years to understand this problem and then see how we can mitigate it.
So we've talked about optical networks and optical interconnect at this scale, even photonic I/O like die-to-die optics on the podcast. We've talked about this before. But tell us why, from your perspective, fiber might not be the best choice for every part of the network.
Yeah, so fiber is amazing that it's able to span such long distances. So these data centers are quite physically large. Some that I've been in are up to 1 kilometer long. And so you need several kilometer links, and the only way to do that is in the optical domain. You can't send copper signals at these speeds, several kilometers. But a lot of the links are much, much shorter distance than that. And so the scale-up network, as I mentioned, is today inside of the rack. And maybe an interesting aside is the reason the industry went to liquid cooling and went to all this pain is to keep the scale-up network inside of the rack. And it's been a lot of pain to add liquid cooling to the data center, but it allows us to have this enormously dense scale-up domain inside of one rack in passive copper. When passive copper no longer does a job, the next best choice is to go to active copper, what we call active electrical cables, which are copper cables that have retimers in them. We started building these some time ago. They don't have to do the electrical to optical conversion, and so they end up being much lower power, much more reliable, and also less expensive than optical solutions. But they can't go unlimited distances, and they do actually have a reasonable amount of bulk because they're copper cables. Once AECs no longer do the deal, our customers are forced to go to optical. And so generally our customers say, we use optical when we have to, we use copper when we can.
Can you tell me a little bit more about how soft errors arise in optical networks, and a bit more about what the problem really is?
Yeah, so there's 2 kinds of optics. There's optics that are called AECs, which are sort of closed-ended optics. So you have a connector on both ends, you have a fixed piece of fiber in between. Those aren't actually used very commonly in data centers because it's really inconvenient to fish them around and kind of loom them through the system, especially when they become 10 or 20 meters long. Most data centers use single-mode optics, which are typically made with pluggables. And so pluggables mean you have a transceiver, you plug a patch cable into that, then that might go to a patch panel, then it might go to some structured cabling, which is kind of in the architecture of the data center, and something similar on the far side. So soft errors occur for quite a few different reasons, but maybe the number one reason is optical link issues. So you can get dust in those optical connectors, which causes reflections back, and those reflections end up having waveforms that kind of sit on top of each other. Even if you're only reflecting 1% of the light, it can distort the signal and make it harder to recover. In addition to that, inside of the transceiver, you can have alignment issues where you're basically trying to align the fiber to the lasers and the photodetectors that are sending and receiving that data. And that can be somewhat temperature sensitive. And so in GPU clusters, we talked about these periods of activity and these periods of idle. The fans on the GPU go from absolutely full blast, jet engine loud, to more of an idle state. And that causes a tremendous temperature gradient on the optics, which is not something we ever saw in the general compute world. That can be a cause of this. Another cause of this is something as simple as ESD. So ESD is something that we've been dealing with as an electronics industry for a long time. But when we put these really high-speed SERDES on, these 100 gigabit or in the future 200 gigabit per lane SERDES, you can't just have a set of protection diodes on there. It's way too much capacitance. And so the pins are much, much more sensitive. And technicians, although they are often careful, aren't necessarily careful enough. And so sometimes you get ESD damage, which can cause latent failures. Maybe last thing is, in order to make these high-speed SERDES work, both on the electrical and optical side, you're constantly doing software compensation because you're getting into nonlinear regions. So when voltages change or temperatures change or optical signal levels change, you're constantly compensating for that. And those compensation algorithms, in some cases, aren't perfect. And so they don't necessarily have complete linearity.
Okay. Some of these things that you're talking about, like ESD and temperature gradients, those would apply equally to copper. How is copper able to withstand it, or how do you solve this problem in copper?
Yeah, sure. So the temperature gradients, copper's not having to do nearly as much work because we're not doing that electrical to optical conversion. So there aren't nearly as many levels of compensation. And Credo's AECs, we really beat on them before we give them to customers. We have quite a large lab in Taiwan with a bunch of thermal chambers, and we try hard to break them. And so because it's a closed system, we're really able to do that. Optics, as I mentioned, are patch panel based. And in many cases, it's not necessarily even the same optics vendor on either side of the link. They have to interoperate with each other. So it's a much more complicated system to stabilize. ESD is an interesting one. I think we might get into this later. One of the things Credo's known for is actually using legacy nodes of technology. So we make SERDES, say an N12 node, that are as good as our competitors' N7 or N5 node products. That has some real cost and availability advantages. Also turns out to have ESD advantages because older nodes tend to be more robust against ESD.
Yeah, awesome, thanks. So we've been talking a little bit about AECs, which is really what we wanted to talk about today. But just in case somebody's listening and this is the first time they're hearing the word AEC, could you spell it out for us? What are we actually talking about when we talk about AECs?
Yeah, sure. So we're talking about an active electrical cable. That's what AEC stands for. So it's a copper cable which has standard connectors on the end, but it has a retimer in the ends. Mm-hmm. And so what the retimer does is it fully recovers the signal all the way back to the digital domain, pushes it into a FIFO, and then retransmits it. And so that recovers our full signal budget, our jitter budget, our link quality budget, everything about that budget is fully recovered. So if you can think between two hosts, if you just ran a passive copper cable, you'd have sort of one analog link there. In an AEC, because you're adding two of these retimers, one at each end, you're basically breaking that link into three pieces. One of those pieces is really well understood. It's the cable that we ship with, and then the other one are much smaller. They're the host links. And so that allows you to stretch the distance you can run, or in some cases, just make the cable a lot thinner than you could if you were using a passive copper cable.
So one of your advantages, as I understand it, is energy efficiency, even compared to optical networks. Please, I'm interested to hear how this energy efficiency comes out.
Optical networks, because you have to do this electrical to optical conversion, tend to burn about 50% more power than active electrical cables. And so just in an apples to apples basis, you're burning much more power to go into the optical domain. You can of course go a further distance. So if you're going 2 kilometers, you have no choice. But if you're keeping it within about say a 7-meter reach, we can save an enormous amount of power in AECs.
But 50%?
50% is a lot, right?
50% is a lot, yeah. Was it the scale of clusters that made you come up with the idea for AECs, or that made you start making AECs, or where did this AEC idea actually stem from?
It sort of goes back to the beginning of the company. Even back at the beginning of the company, 12 or 15 years ago, people were saying that copper is a dead technology and there's no reason to invest in it. But what we see time and time again is if there's any way to make copper work, our customers will do it. And as we talked about, NVIDIA went to enormous efforts in order to make the scale-up backplane on the NVL72 racks work. And so AECs are a way of extending copper, and we saw that would become essential as we got to 25 gig per lane speeds, 50 gig per lane speeds. Now we're in mass production on 100 gig per lane, and next year 200 gig per lane speeds. And so it allows us to make a cable that goes 3 or 4 times as far as you can in the passive space, or in some cases just make a cable that's enormously thinner for in-rack connectivity. And those are two of the use cases that our customers have absolutely driven us towards.
So My experience of learning about hyperscalers hardware and hyperscalers data center setups is that they're all very, very custom. They all have very specific needs and they all know exactly what they want to do. How do you make an AEC that meets all the needs of all the different hyperscalers? Is it a family, or are we talking about the same cable really for everyone?
Yeah. So when we started making AECs, we thought it would be the same cable for everyone. We were deeply wrong.
Yeah.
And so we started making a generic family of cables, and then we find out that each hyperscaler actually wants something quite different. And so they have, something unique about their network that they want to propagate, and that first level of connectivity turns out to be really important for them. So it could be that they want, some proprietary timing signal developed. An interesting use case we spent some time in is it's difficult to synchronize firmware upgrades from both ends of the cable, because typically hyperscalers will have one group which is in charge of the CPUs or the GPUs and a different group in charge of networking. So to come in at the same time and upgrade firmware is really inconvenient for them. So if we can make a cable that's upgradable from just one end so that one of those two teams can own it rather than both of them having to collaborate, that turns out to be a really interesting use case. The first big production cable we had was actually with Microsoft. And so Microsoft had an interesting challenge in their general compute. They were using a single top-of-rack switch per rack. And so if that top-of-rack switch failed, the blast radius was the whole rack. And it would take down the entire rack, which wasn't good for their customers. So the only option they had at the time would be to have a redundant rack in order to achieve high rel, which is quite expensive. They asked us to build a cable which would transparently manage the failover from one top-of-rack switch to another one. So normally in the past that work had been done by the server, but their servers were all built for top-of-rack switches and they didn't want to have to, or for a single top-of-rack switch, they didn't want to have to change that. And so we built a cable for them, maybe the most complex AEC that's ever been developed, which actually has a layer 2 switch in it and is able to transparently manage that failover, such that the servers aren't even aware that they're talking to two TORs. The cable just takes care of it transparently to the user. In the end, I think we had the conversion time down to a small number of milliseconds, so we wouldn't even drop frames on a video stream.
Awesome. So I understand your latest gen is called Zero Flap. I'm guessing this is related to the link flap problem we were talking about earlier. Tell us a little bit about what that is and how it works.
Yeah, so we've spent a lot of time working on our AECs, and we're fortunate in the general compute space, we've shipped a lot of AECs. And so we were able to look at the field data that we had amassed. We had about 6 or 7 billion hours of field data from the AECs that we'd shipped. And our customers are, they're pretty demanding. They're not shy about picking up the phone if we have link flap issues or other problems. And so our AECs have had failures. AECs do fail, although not very often. But we've had no cases of unexpected link flap in our AECs. So this soft link flap issue that we see in optics all the time. And so we were able to characterize this and start to understand, why. But the most important thing for our customers is that we have a cable that doesn't flap. It's not subject to these soft link flaps the way optics are. And as we started to look at the optics space, the rate of soft link flaps is actually pretty high. It's maybe 100 or 1,000 times higher than the rate of hardware failures. So they're happening all the time in a large data center. So if we can have a copper cable that doesn't subject them to this at all, it actually makes a material impact on data center reliability.
I mean, we still need optics for longer distances. The copper, we're talking about the shorter distances. What is the distance limit for copper? At what point do we need to go to optics? And do you see that balance shifting as we go forward?
Yeah, we can go up to 7 meters today at 100 gig per lane products. We'll hope to hold that in future generations. But there's many cases in the data center where you need to go longer distances than that. One of the things that the migration to liquid cooling has done is it's really densified the data centers. So it used to be that in a data center, you might only have 8 GPUs in a rack because you could only support 10 kilowatts of thermal load. And so a pod of GPUs, which is sort of the GPUs combined with the first level of switching, might be 20 meters long. And so that first level of interconnect used to need 20 meters of distance. Now with liquid cooling, it's common that first level of interconnect only needs 5 meters of distance. And as rack densities increase, it's probable that first level of interconnect is actually going to get even closer. There might be one network rack per GPU rack, and they just end up side by side with each other.
Yeah. So you mentioned earlier that Credo designs the whole of the AEC. You're making chips, you build the system, you're making software. Tell me about why that works better for you, or why did you feel it was necessary to basically take on the whole stack yourselves?
Yeah. So when we first got into AECs, we tried actually just selling our retimer chip to a cable company. And one of our customers paired us up with a cable company, and we thought that would be a great way to go to market. But we quickly found that the cable company needed us to design the circuit board, the paddle card that goes in, and they needed us to write all the software. They needed us to develop the test solution. When there were debug issues, they needed us to manage them. And it became pretty clear to us that there weren't any cable companies who had the ability to do this. And so in order to get the product to market 8 years ago, we took this entirely vertical. But once we started engaging with the hyperscalers and understanding that, in fact, they all wanted something special, then the math just, it completely made sense. Because we can have the guy who's designing the cable and the guy who's writing the firmware and the guy who architected the chip all right next to each other, solving problems so quickly. Whereas if those are spread across 3 different companies, it just takes too long. And so we can get solutions to market that are better, faster, and less expensive than you can in this disaggregated model.
So you are a chip designer. I mean, Credo is one of only a small number of companies that makes a high-speed SERDES, which I understand you offer as IP and also as chiplets. Tell us a little bit about what differentiates your SERDES from other people's, and why offer it in those 2 form factors, IP and chiplets.
Yeah. So Credo started out licensing SERDES. It's actually a really good way to bootstrap a company because it makes it a bit like a software company. So you're not having to spend all the capital to deploy hardware. You design this circuit, and then you hopefully license it out to many companies. The folks who began the company are they're absolutely the top SERDES designers in the world. And so what they do is many people take kind of standard TSMC cells and build them together into an analog circuit, respect all of the design rules, and then you end up with a very inefficient high power SERDES. If you design your own cells and you understand, the characterization of what's happening, you can end up with something that's, maybe 30 or 50% less power. And in our case, then you can run it in an older generation. And so we call that our N-1 advantage. When other folks are shipping in 3 or 5 nanometers, we'll be shipping in, say 12 or 7 or maybe 5 nanometers as well. And so that's really the core technology that Credo brings from a SERDES standpoint. We do continue to license that out to select customers today, but more and more our focus is on delivering complete products.
Looking a bit further into the future then, if we can extend the life of copper, copper can be more power efficient than optical, and now we've got zero flap, and we can make sure it's very reliable as well. We've talked before on the podcast about enabling scale with optical networks and optical communication, but how do you see this copper and AEC kind of shaping the economics and the scale of these type of huge clusters going forward?
Yeah, I think leading hyperscalers now have standardized on AEC for the first level of interconnect. And this is really the first time we're actually seeing copper displace optical. It's always been the other way around. And so we're seeing that first level of interconnect, which, as I mentioned, when it was an air-cooled system and it was 20 meters, it had to be optical. Now it can be active electrical cables, and you can end up with just a much better solution all around. And I think we've got most of the top hyperscalers have already migrated to that architecture at this point. And so we're starting to have to design the building around the interconnect. And so that is the challenge, is you have to intersect the design cycle early on because the fuse is relatively long to get this to market.
For sure. Do you see a limit to how big GPU clusters or ASIC clusters potentially could realistically get, or will we keep innovating and networking to push that ceiling higher?
Certainly, we see some mechanical limits on the building and how much power we can bring into the building, and perhaps some economic limits as to how many assets you want to put inside sort of a certain, blast radius, so to say. But many of our customers are heading towards more than 100,000 GPUs in a single building, and then starting to build clusters of buildings in the same campus to get well north of 1 million GPUs in a campus. It's a pretty tremendous thing if you think of the amount of infrastructure that's landed there and the amount of power consumption that goes into that.
Yeah, absolutely. Do you think we can ever reach 100% utilization of these clusters, or how high can we go?
Yeah, we'll never get to 100% utilization, but if we look back in time, we could say what's possible. So when we had small clusters where the odds of having a failure were small, we were up in the mid-90s. As the clusters have gotten bigger, we've gotten down into the low 80s. So I think if we can all collectively work on reliability, we have an opportunity to get back into the mid-90s, and that may be an upper limit, given that we still do need maintenance. These are some of the most complex devices ever developed by man. Millions of computers all interacting in real time with each other, and sort of sparing on the fly and having some redundancy. But we need to really, really focus on reliability. Otherwise, we're going to end up with a fundamental scaling limit here.
How do you see the needs of enterprise clusters developing? I think from my perspective, it seems like enterprises might want to build bigger clusters or potentially bigger clusters than they have now. Would that look like more of a standard, like an off-the-shelf product for you versus the hyperscalers? Or how do you see that enterprise market potentially developing?
Yeah, it's a really interesting discussion. So, why would an enterprise want to build their own cluster rather than renting one from somebody who does this for a living? It's probably because they're so concerned about the data that's inside of it that they don't want to let it out of their control at all. And so the enterprise clusters that we've seen proposed tend to be a little bit smaller in scale than the hyperscalers. We don't see sort of gigawatt level enterprise clusters proposed yet. Perhaps that'll happen in the future. And so the benefit is they can learn from all of this pain that the hyperscalers are going through and hopefully have something at sort of reasonable scale that's much more reliable for them. Because they're typically starting with some base model and then they're going to be training and tuning it to their specific needs. They're not usually starting from scratch.
Do you think there are some workloads, beyond AI? AI is a classic use case right now, but maybe it's more like supercomputing, HPC, or quantum computing. Do you think these other types of workloads are also going to help drive networking innovation?
I think networking is becoming simply more and more important as we focus on larger and larger problems, because you can't solve it inside of a single piece of silicon or a single rack or a single row, and you need all of these units working together simultaneously. And so network is the glue that holds that together, or, the plumbing that holds it together. Yeah. What happens in the world of quantum has a lot of uncertainty in it, but I'm very excited to learn more and read as that space develops.
Absolutely. Okay, so if someone's listening to this and they want to find out more about Credo, about your AECs, about the zero flap technology or anything else, tell us about where they should go.
Yeah, sure. So actually, if you're listening to this live, next week, we have a large show, the Open Compute Global Summit in San Jose. We're going to be introducing some interesting optical products in our zero flap line. So we're excited to show you those and present on those. Otherwise, you can always get the best information at credosemi.com, or you can follow us on various social media.
Don, an absolute pleasure. Thank you so much.
Thank you for having me.
Thank you so much, Don Barnetson, for the intriguing conversation about copper versus optics for reliability and scale-up networks. This episode of AI with Sally was brought to you by Credo Semiconductor, and thank you so much, Credo, for sponsoring us. You can catch Credo Semiconductor at their booth at OCP this week, October 14th to 16th at the San Jose Convention Center, and they are at booth B23. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. If you're listening to this on the podcast page at eetimes.com, links to articles on topics we've discussed are shown on your left. AI with Sally is brought to you by Aspen Core Media. The host is Sally Ward-Foxton and the producer is James Eade. Thank you for listening.